first software today. I'm going to talk about what it is. I'm going to talk about what's different about local first from cloud first systems. I'm going to show you it working. So I'm going to show active-active replication between Postgres and SQLite in the web browser through Elixir. And then I'm going to talk about some of the challenges and trade-offs in adopting local first as a development paradigm. And then I'm also going to touch on both how we use Elixir in the implementation of our system and how that influences the scalability characteristics, and also how you can build local first applications on top of standard Elixir systems like Phoenix and Ecto. There is also an element of audience participation. It's not quite as much as the Elm glue code talk, if you caught that one, but be ready, because it's crucial to the progress of the demo, so I'm going to need your help at some point. Hey, welcome. So, I'll just restart this one. So basically, what is local first? So local first, there's a great manifesto by Ink and Switch that talks a lot about it as a paradigm, and there's quite a lot of different aspects of it. Basically, what it boils down to is a model where your application code talks to a local embedded database, and then data syncs in the background. And I think one of the most interesting ways of understanding it, is as a systemic solution to state transfer. So if you're anything like me, I'm like a generalist developer. I've probably spent far too much of my career moving data from one side of the network to the other, and you get involved in everything from CRUD and serialization and validation and checking HTTP status response codes and writing rollback handlers if stuff gets rejected on the server. And also, if you think about when you're starting developing an application, so one of the most fundamental choices you make when you're building any kind of application is how you're doing state transfer. So do I build it on LiveView? Do I build it on GraphQL, right? And it's this fundamental concern basically at the heart of all software development. And interestingly, I think every time state transfer has evolved, it's transformed the way that we all build applications. So summary of the kind of journey of state transfer across the internet, we started with forms, then we got Ajax and could build single-page applications. Ajax kind of standardized on REST, but REST is still basically imperative state transfer, right? You're writing explicit code to choose how data moves across the network. And then comes along GraphQL, some other similar systems, and it starts to abstract state transfer out of the application domain into the core system. And then you can have system optimization. So in GraphQL's case, what you get is fragment containers that are bound to your component, and then you have something like the relay compiler, and that is able to build out, aggregate the data that's required to fulfill a query at the top level of your root, and so the system optimizes that like initial fetch of data into your app. Now with local first, it's the kind of extension of that. We see it as like the natural next evolution and the end game of state transfer, whereas instead of just abstracting out that initial fetch and network transfer, it fully moves state transfer out of your application domain and into a declarative domain. And so what you get with that is that instead of just optimizing, say, a top-level fetch for a root, the system can take over and start to optimize a broader range of concerns, including things like data transfer, data placement, trade-offs between, say, consistency, availability, resource usage. And so, like a lot of the core technology that this kind of approach builds on are things like CRDTs and developments in eventually consistent database systems. One of the key research groups around this is a group around Joe Hellerstein at Berkeley. They developed like Calm and the Hydro project and things. And this is one of their recent papers that's more of a vision paper for where this stuff goes next. And what they articulate is a future of cloud programming where you move your programs into this declarative space, and then essentially the system or AI can optimize between concerns like consistency, availability, and resource usage. And so that's one of the things that we see in terms of where this goes as the next step and why this is interesting as a development paradigm, that if you think about the term data infrastructure and what kind of optimizing data infrastructure has meant over the past decade, it's tended to refer to things like sort of streaming data pipelines and kind of big data and OLAP applications. And the next step in data infrastructure is to kind of move a bunch of that into this domain of like reactive state transfer mesh for OLTP applications. So I think, I mean, if that's a kind of big picture, coming more to the sort of present, like where does it start? Sort of what are the drivers for adoption of local first? So there's a range of things like sort of user ownership and privacy by design, but the real practical value propositions are A, resilience. So because of the model, your application, a local first application, it works when the network is down, it works when the back end is down, it defaults to working instead of being default to broken. And also, so you take the network off the interaction path, your app code just talks to the local embedded database, so it feels instant, you don't have the kind of lag and loading spinners, and then because you're having to handle offline capability and background sync, you have to build things in such a way that it supports real-time multi-user, and you're doing active-active replication, and so you get this combination of instant reactivity, real-time multi-user, and conflict-free offline, which when you combine them, is kind of the best possible combination of user experience. And when you look at, say, consumer-grade, prosumer-grade systems with cutting-edge UX, things like Figma, things like Linear, things like Superhuman, the question is like, how do you build applications to that kind of grade? And that's what Local First can do. Actually, as a paradigm, it allows you to build Figma or Linear-like systems that deliver this kind of combination of UX affordances. So that's a bit of intro about local first. So what is ElectricSQL? We're kind of like Hasura for local first. So we are explicitly a brownfield strategy to local first. We're trying to provide an adoption pathway for existing systems and existing applications that are based on Postgres. You basically drop ElectricSQL on as a sync layer, and it provides basically instant local first APIs as a kind of replacement for your state transfer layer. So you have Postgres with your existing data model on the back end, and then you just get magic live data that you can bind to your components on the front end. I mean, just to talk about a couple of aspects of it. So one of the things is you move from, I talked about GraphQL, about, say, optimizing that data fetch, and you then sort of say maybe cache the data in some kind of store. With this system, you move to a sort of fully live, active-active model, right? So you need to build your application around a paradigm like subscriptions or live queries, because basically you will build it so your components react to writes that you make to the local database, but also you have active-active replication, so changes could be made by other users, changes can come from Postgres. So you basically sort of wire up live data to your applications instead of making kind of one-off imperative fetches. And we then have this pattern particularly where we use Postgres at the center as a kind of control plane. So you can use it both to publish content, so you can insert or update content into Postgres and it streams out through the replication machinery onto the local applications. And also, if you want to, optionally, you can use it to aggregate data or a subset of data back from the local devices into a central database. And also importantly, what it does is you can evolve the schema, like the database schema of the local first applications by changing the database schema of Postgres. So you just apply migrations normally using any existing migration tooling to Postgres, and then those migrations both stream out through the replication pipeline automatically into the local applications, and also we pick up on that and allow you to build out a type-safe data access library just based on the existing schema of the database. So, what I'm going to do now is I'm going to try and jump out to a live demo. So wish me luck, and let's hope things work. But what I'm going to show is basically a kind of standard, very simple Elixir application that's talking to Postgres. And I'm going to show actually just a web application, and I'm going to show you how the kind of data streams between the two, demonstrating some of these patterns around content publishing and interacting on top of the data, and also the evolution of the migrations. So give us a sec. Go. Can you read that code size? Is that okay? At the back? I'm getting some, let me just bump it, sorry. Nodding head, good. Okay, so just to very quickly talk you through some code here. So this is like, this, as you'll see, is like a standard Elixir application. It has an Ecto repository for interacting with Postgres. We have a worker, which is basically just a gen server that is designed to pull down data from the GitHub API. And we have a webhook controller that takes webhook notifications when you start our GitHub repository. And the whole thing is a sort of silly beers for stars application where the idea is that we want to thank everybody who stars our repository on GitHub by offering them a beer. And so this is a system by which we can allocate you beers. And then at the end of the conference, when we finish, we're going to meet up in the lobby and we're going for craft beers in a place called, I think, Multiculti nearby. So everybody's welcome and the beers are on us, as long as you engage in the audience participation. So there's always a quid pro quo in the modern world. So for instance, that was sort of showing you a little bit of the Elixir application. Here, for instance, these are just standard ecto migrations that should look quite familiar for like defining the database tables, including like relational structure. And then over on the client side, we have a standard React application developed in TypeScript. So it's just a normal React application. Here, for example, is one of the widgets that show you how you use the kind of data integration. So what we do is we sort of electrify your underlying SQLite driver. We provide this data access client. It's basically modeled on the Prisma API extended for live queries. You also have the opportunity just to drop down to raw SQL, so you don't have to use the kind of query builder stuff if you don't want to, and we still maintain all the live subscriptions on the raw SQL. But basically, you get a handle on the DB through like a React context provider. And then we have a use live query hook, and this is where you're just defining any database query that you want. It's full SQL against SQLite. So you can do absolutely anything you want against a standard SQL database. And then these results just basically stay in sync wherever the data changes, no matter whether that's like locally or coming in over the replication stream. There's people coming in early. It's exciting already. Hey. keep it coming. And then, so here, for example, just to show, like what we've got is a SUDI component which is rendering a listing of beers, and then there's two buttons to pour or empty the beer. As you can see here for this add method, for instance, what you go is you go dbbeers.create. You don't have to do any additional reactivity stuff. You don't do any state management paradigm. You just work directly with the local database and everything just works as magic, right? So it's trying to just minimize all of the kind of in-application state management stuff to just work with the SQL database and everything stays live. So that's kind of the code. I mean, what I've got running here is I have ngrok to just have some incoming connections. I've got our local stack, which is the sync service and Postgres. So here, for instance, this is the Postgres database. I've set up the app to start with the ecto migrations for a beers and stars table. I'm running a Phoenix server, which is receiving things through ngrok, which is where these stars are being from. Thank you very much. And then we've got a client application running here, running the client. And then basically I've got these two tabs open. If I just go here, maybe make these a touch bigger. So what we've just got is I've just got two browser windows open. One's a normal one, one's incognito, so they're using different local SQLite databases. It's just like having different user devices. And as you can see, everything just basically stays in sync. So the content that you're seeing appearing in here so far is basically coming in through webhooks into the Phoenix application. Phoenix is writing it into Postgres, and it just magically appears in the application. What you can then do is, just in the application here, we could start, say, pouring beers. As you see, if you interact in one, it's just real-time multi-user. It kind of syncs to the other. Also, the actions are just instant, right? There's no, as I say, there's no network on the interaction path. Everything's just a local write. What we also have is we have the capability to tolerate the connection going on and off. So we have this offline support. So I've just switched off the connectivity in the right-hand application here. If I say pour a beer here and empty these beers here, if I then switch on the connectivity, you see that both sides have end up in a consistent state. So it's eventual consistency. It's actually the strongest possible mode of eventual consistency, which I'll talk about in a bit. And then what we can do is, I'll show you as well. So from Postgres, it's not just that, so there's basically one beer you can see in the app. If I go select count all from beers, there's one beer. If we go, say, insert into beers, values, gen random UID, as you can see, you write it into Postgres, it just instantly appears in all of the local clients. So this is how, like, it's basically this bidirectional replication, and stuff just streams out from Postgres kind of as a content publishing or content management kind of system. Now, if we just sort of trade that up a little bit, I've got a couple of mixed tasks here. So let's say that we want to go, let's sync down everybody who has started the repository on GitHub so far. Now this is just pulling in batches of, that just pulled in batches of 100 people. Actually, you didn't see them come in because there were people at the top of the listings, but basically it all just streams in transactionally. What I can do is say thank you very much to everybody who has starred us so far, allocate beers. In this case, again, you'll just see how it just comes through basically transactionally at the same time. So that was like 650 or 700 stars, and you just allocate them all, and it just comes through the replication stream transactionally. So it's these atomic kind of changes. So you get kind of standard atomic semantics on top of standard open source SQL with just pure Postgres, any Postgres on the back end, and just standard SQLite on the front end. Now, so this was the moment where I was going to say open up for user participation. So if you haven't starred us so far, it'd be super, super helpful if you would like to go to our repository and star us now, and you'll see it coming through as you've already seen. And then you'll see that what I can do is, as you come in, I can start to allocate beers to the content. So it's this sort of pattern of interacting on top of data that would aggregate through. A lot of applications today will do things like aggregate different data sources. And then you're looking to provide some sort of like interactive or collaborative experience on top of that. So this is a really nice pattern where you can just basically stream stuff into Postgres as a database. Everything comes out of Postgres into these local applications, and then people can collaborate on top of it with the kind of results streaming back into the main database. So thank you very much, awesome. So I can try and keep up and allocate beers to everybody. I'll run my script again, try and keep up. But cool, I hope that gives you an idea of a bunch of the sort of ways in which the data streams between the different systems. The one other thing that I really wanted to show is, so for instance here, when you update your Postgres schema, what actually happens is it comes through the replication stream using some clever stuff, and we actually build it out to a Prisma schema, and then we generate out a type-safe client, as you can see here. So this basically uses Zod, and you end up with a type-safe data access library built on your DDL schema. If we went to this like beers widget and kind of hovered here, for instance, got this one, right? Does that? Yeah. Okay, sorry. I'll be talking too fast. Cool, so yeah, I was basically just I was showing that you get this basically type-safe client automatically built off the Postgres schema. So if what we now do is say go down to the migrations, so here, just gonna enable a pre-made migration, because once you've had a bunch of beer, what you really want to have is some pizza. So let's create a pizzas table. So I can go here and I go mix ecto.migrate. That just applies the migration. If we come back to Postgres, what we can see here is we now have a pizzas table. Now that migration is already streamed into the SQLite databases within the local applications. But what we can also do then is come back in our, not quite sure what that is. So if we come back here and go electric migrate, this is in our development environment, we can now pull in the latest schema into our code, so we basically update our local development environment to match the database schema. And then, so that basically comes in. And if we come here, you see that there's now a pizzas table, and these generated types now kind of understand it. So if we went into our application, again, I've got a little pre-made pizza widget. We save that. I think I just need to rerun the application here. refresh the page. And as you see, we've now got the ability to, we can pour beers, we can drink them, then we get hungry, make some pizzas, and eat them. Yeah. So that was the end of the demo. What I really wanted to show with that last bit is just basically the ability to evolve the schema at runtime by applying the DDL migrations to Postgres. And there are obviously some nuances about just sort of how you manage your code deployment to match the evolution of the schema, and that's all sort of part of what we're working on as a developer experience. I will switch back now to the presentation. Let me just do the display. Cool. So I hope that gives you some idea of I guess sort of some of the capabilities of the paradigm and some of the value propositions or affordances it can deliver. What I also wanted to talk about is just a bit realistically about some of the trade-offs and challenges with it as well. So if you're going to port application development to local first and say, right, let's swap out GraphQL for this, what's actually the reality of building local first applications? So I mean, one of the obvious challenges that you also get with other, say, back-end as a service platforms is that you lose the back-end, right? And so what you typically do for business logic is you'll move some of the business logic into your front-end application, but you also move some of it into some kind of either database rules or event sourcing. There's a whole bunch of ways of basically running back-end code off of database change events that already exist. One of the nice ones in Elixir, for example, is you can write into a table directly in your client application and then have Oban just picking that up as a job queue on the back end, because Oban just works with jobs that are inserted into Postgres. So you can just basically enqueue back-end jobs directly from the front end, or you can tap into something like Postgres logical replication, or you could put something more comprehensive on, like, for instance, Materialize or Debezium. I mean, there's all sorts of existing tooling to basically sort of trigger event sourcing. One of the other challenges with losing the back end is you don't have that kind of trusted execution environment for your things like authorization and validation code. And so again, like systems like, say, Firebase and Couch have done for quite a long time, you have to encode certain things into database rules. Now, as a Postgres-based system, you immediately think of something like row-level security, which is what systems like, say, Superbase or Hasura use. Now, we don't actually do that, partly because, A, it's slightly, in terms of porting your authorization or middleware logic, it's a slightly different concern than just putting sort of basic check constraints against your database schema, because typically your database connection is like a database user, but you want to have some sort of authentication or request context from an actual application user. And so what we do is we basically we have a similar rule-based system, but we actually run the authorization in this kind of middle layer here, which is our core Elixir sync service. And that's primarily because, A, we wanted to give a rule system that allows you to express the type of concerns you would typically be porting over from something like a plug, but also in terms of providing the authentication context. The only way to provide that authentication context within the database itself would be through an extension, and that radically limits the Postgres systems that this can work with. So we've built all of this system to work with any Postgres that supports logical replication. And that includes all of the managed services from all of the major cloud providers. You don't have to have a whitelisted extension or a custom Postgres to run this. This just integrates directly with any existing Postgres that you're running. And logical replication has been enabled for, I think, 3 or 4 major versions now. Interestingly, I mean, this gives you an idea of the kind of basically what we have now is you just have Postgres, you have this Elixir sync service, and then you have the client. When we actually started the project, we started off building on a system called Antidote DB, which was a beam-based, geo-distributed, multi-region database engineered to deliver the best possible consistency mode for an AP database system. Which was awesome, but it introduced an awful lot of operational complexity because you had to basically provide durability or availability guarantees for both your core database, but also the sync layer. And so what we worked very hard on is being able to strip out that kind of layer and do this model just directly on pure Postgres. So Postgres is not what you would think of as a natural sort of CRDT or kind of snapshot-aware database, because it doesn't have the concept of being able to request data at a certain snapshot. But we've been able to basically mirror the same semantics that you have with a custom CRDT database directly on top of vanilla Postgres. And so that's why what we've been able to now do is basically say you run what is very similar to a stateless Elixir service. So it's very simple just to self-host. It does have some state because we maintain information that allows the way we handle the replication streams to be efficient, but that state is rebuildable from Postgres. So there's no durability requirement for the Elixir service. And generally, with the shift of the things like authorization and rule logic out of the database layer into the middle layer, what it means is for the whole system is if you're trying to say scale out Postgres, you've got different solutions. Like a lot of the solutions today would be things like say Cockroach or Yugabyte, and you end up running like 20 nodes, and you have coordination to maintain consistency, and you have to have a really big operation to gain some kind of throughput benefit compared to a single Postgres. What this does is it takes all of the query workload off of the database, it takes the authorization workload off of the database, and it puts the query workload into the client and the authorization into the middle layer. So you can go enormously further on just a single vertically scaled Postgres instance than you can with other solutions. And it actually gives you optimal caching from the perspective of where the kind of query workload and the data flows hit, compared with other solutions that are trying to scale out some sort of high availability story for Postgres. And as I mentioned, I mean, as you can see here, I mentioned about the sort of durability and then the rebuildability of the sync service layer. Also, just like in this kind of topology, you have a natural kind of size of data that you would typically store on the different nodes. So it's an active-active system. Every node is a source of truth, but Postgres is the source of durability in the system. And then, because particularly when you go to the local devices, you're going over the public internet, they've got much less storage, much less memory, and you want less. You want to transfer less data or a subset of the data onto the local device. What we've worked out very hard as a project is basically designing and implementing a model that allows you to implement whichever strategies you want to optimize the way that you do dynamic partial replication of data from the central Postgres onto the local devices. So if you look at this, this is like a sort of range of, say, sort of typical kind of sync models or kind of data loading strategies that you might want to implement. You have, say, on one side, it's whole database sync. Let's just sync the entire database. Schema-based sync would be something like, let's just sync these tables. Row-based or content-based sync is when you say it's these tables, but also just this subset of rows in them. Like a live query would be something where you say query the back end, take the results, and you want to keep that result set in sync if any data changes on the back end. A pinned query would be like query Postgres, take the data into your application and make sure that the same data is there if the user goes back to the same page. And an ephemeral query is I just want to hit the database and kind of throw it away. And so what we tried to do is design a system that allows you to basically implement any of those strategies in your application. And so what we have for that is a model that we call shape-based replication. So like a shape is basically a subset of data that you replicate out of the larger Postgres database onto the local device. Now you can see the API here. It's sort of similar to what I was showing you in terms of the query API. And it's also, the shape function is also built into that type-safe data access client. You start off by saying it's table scoped. So db.projects, in this case projects is a table. You then have you can then add where clauses to basically filter down the top level resources. So in this case, I want just like one project, or you could have an array of projects that you want to sync in. And then this include tree is like an association graph. So you're basically not just saying, right, I want to sync in these rows from this table, these rows from this table in like separate commands. You're saying, right, when I sync in a Figma design, I want to sync in all of the shapes and all of the comments and all the stuff underneath it. So you sort of define that kind of bag of data that you want to sort of pull in one go and say, that's the shape of data that I want synced into my application, so that I can then have interactive offline functionality that's not necessarily just on like a particular query, but you're maybe syncing more data so that the user can navigate across different parts of the application. And then just at the bottom here, we have like what we call retention and subscription semantics. So do you want to keep that shape subscription live? Is it just ephemeral? Do you want to just keep it? What happens if there's contention on the storage on the device? Which data should be thrown away first and then refetched if necessary? So you can basically sort of express all of the strategies on the previous slide with this API. And this API is available to a front-end developer. So what we have on the server side is we have what I showed you a little bit of an example of those permission rules, which is where in the database side you control authorization of data access. Whereas on the front end, what you're trying to do is give a front-end developer an expressive primitive to be able to choose exactly how they craft how data syncs onto the app. Because you might want to change a few fields, you don't want to have to go back and do some DDL change request in order to say, I want to change my query. You want to be able to experiment and optimize with the way that data comes over the network. So we tried to sort of split the right APIs for the right user on either side of the system and make it as expressive as possible for the front-end developer. A couple of other interesting aspects is, so this is basically the ability to derive a synced shape of data from the way in which you're binding data to your components. So I mentioned about, say, GraphQL and Relay. GraphQL has like fragment containers. You have the Relay compiler that just automatically like sort of aggregates all of your fragments from a component hierarchy into the shape of the query for the top level fetch. And we can do the same. So this is something that we're working on. We haven't implemented yet, but conceptually we have the ability to say you're binding these live queries to your components, and we can have a similar compiler phase that basically processes those, derives out the aggregated shape that the components need for a certain part of your application, and then just automatically sync it. So in a sense, what we start off with sort of, say, an imperative primitive to say, or like a function call to say, I want to sync the shape of data, we can increasingly derive those automatically from the way in which you're programming with your app. And then one of the other key challenges is discovery. So when you build applications, if you're saying, right, I want to sync in this Figma design, it makes sense to go, so give me all that rag bag of data. But what if you don't know which Figma design you want to sync? Or you want to do like search or listings? You can do, say, a kind of wide, shallow shape, so you can sync in the data necessary for the listings or for the search index. But in many cases, you want to be able to query data on the back end that's larger than the data that you would choose to sync onto the device. Now, if you do that out of band, so you just go, hey, I'm just going to go query my Postgres, you get the result set, and how do you keep that result set consistent with the data in the database? Because you lose all of your consistency information because you don't have the same, you basically can't preserve causal consistency if you do those out of band queries. So what we've done is we've provided a mechanism to do basically in paradigm arbitrary queries against the Postgres. We take then the result set of that query and we turn that into a shape that stays subscribed to. And then what we plan to do is then add mechanisms on the back end that keep that shape live as new data that would match the query streams in on the back end. So you basically have the ability to do things like full text search over a massive database, get the result set, sync that onto the device, and then keep that kind of offline available and local first. Pause for breath. So just lastly, I'm not going to go into super amount of depth on this because it's a slightly different talk, and it's also a talk that's probably best delivered by another person. But we're obviously operating at this sort of far AP side of the CAP theorem, right? It's local first, you have offline capable applications, it's things like mobile apps. They can get lost behind the sofa with some writes made and reconnect after 2 weeks, and you have to be able to kind of handle those scenarios. So you have all the classic challenges of how do you handle concurrency and overlapping writes in that sort of scenario. And this is the sort of heritage of the project. So we are working with the co-inventors of CRDTs. We're building on a bunch of research into the strongest possible consistency modes for this. And so explicitly, we implement transactional causal plus consistency based on CRDTs. And we're doing real SQL, right? And so real SQL is not just say, how can I keep this particular object in sync? It's referential integrity and unique constraints and check constraints. So these are famously difficult to know how to maintain those kind of invariants for this type of AP database technology. And actually my co-founder and CTO, Walter Belegas, he specialized in his research in building these types of invariant support on top of CRDTs. So he invented the bounded counter, for example, which was one of the first numerical invariants on top of CRDTs. And so we have what we now call rich CRDT techniques, which are a range of techniques that are either conflict-free or introduce some minimum runtime coordination in order to be able to preserve typical relational invariants and constraints. So the example on the side of the slide here is like a referential integrity violation where, so say somebody concurrently deletes a tournament whilst at the same time a player enrolls in it. If you accept both of those rights, you end up with a violation because you're trying to refer to an object that no longer exists. And so compensations, for example, are a technique to resolve that in a conflict-free way where you make sure that you either use an add wins or a remove wins strategy to make sure that you never get a referential integrity violation. And reservations are like a generalization of this bounded counter mechanism that's like a runtime distributed locking mechanism. So particularly with this system as a CRDT-based system, we're trying to provide finality of rights on the local device. So it's not like server authoritative where you sort of do a tentative write and then it can get rejected on the server. You're saying once it's written locally, it's accepted. It may be built on through a concurrent merge operation, but it's only ever built on, not rejected. And so if we want to prevent the write, we have to be able to prevent it kind of at the edge, which is on the local device. And so if you want to maintain something like a different strategy for referential integrity or a unique constraint, you can acquire these distributed locks through this reservation system that means that you have the right to confidently make that. And so it's a sort of system that generalizes distributed locking to introduce the minimum runtime coordination together with this sort of finality of right CRDT system to be able to do relational invariance. And so that's a sort of, in a sense, the general challenges with relational invariance with an AP system. And as I was describing, we have this shape-based sync model, and we do dynamic partial replication. And the moment you have these partial replication boundaries, you get additional challenges around how you maintain the invariance and constraints across them. So how do you maintain referential integrity if you're not syncing the other table? And there's a bunch of kind of edge cases and strategies around this. And also with authorization, so kind of read path authorization is one thing where you're basically filtering data to where it should stream, and that's simpler than write path authorization, where unless you're doing this kind of server authoritative rollbacks, you have big challenges around clients being able to say, operate in the past, and choose to say, this is a concurrent update. And so there's a bunch of challenges there which we're working on to basically be able to provide a sensible authorization model with this consistency and sync model. All of which is basically designed to deliver this, right? So there was a bit of the kind of complexity under the hood from a distributed systems point of view, and there's challenges of adopting the paradigm, but the intention is to be able to say, right, if we can get this stuff solved and we can keep the complexity in the box, what you then get as a development methodology is that you drop this kind of sync system on top of your Postgres, it works with your existing data model, and you can build apps that are instant, naturally real-time multi-user and support conflict-free offline. So that's what we're trying to do. This is us. If what we're doing is interesting, we're explicitly looking for design partners. So we're keen to work with companies who would be wanting to develop apps on this kind of paradigm. So if it seems interesting to you, there's some more information on this next link, and please just let me know. I'm here, and I'm going for beers afterwards. And that's us. So thanks very much.
Thank you so much. And do we have any questions? Yes, we do.
Is there any challenge like dealing with sensitive data, for example, like when sensitive data are replicated locally?
Yes, I mean, so, I mean, I guess one aspect of that is whether you can have some sort of encryption or kind of privacy sort of technology baked into the system. In some cases, where you would need access to the values in order to arbitrate a concurrent merge logic, then it can be challenging to introduce, say, encryption with CRDTs. As it happens, the strategies that we currently use don't have a problem with that, and we're happy to work with opaque values. We haven't currently implemented encryption because it's on the roadmap, and we kind of can do, but you can implement it on top of the system, basically at the edge yourself. But there are, once you get into the details, there are challenges of this model of basically if you're starting to obfuscate data, then sometimes the information is not available to preserve the user intent. Yeah. And there are some really interesting projects that have tackled this type of, say, relational CRDT-based syncing. There's one called CRDT_SQLite, which is built for Dart and Flutter, for instance, which has built-in encryption as a first-class citizen. So there's other sort of similar projects which have attacked the problem from more like a sort of encryption and privacy-first point of view. Whereas, as I said, I guess our focus has been really trying to get this sort of model of dynamic partial replication and the integration between a sort of Postgres as a control plane and the local apps.
Okay.
I was just wondering, like, if I know in the evening I'm getting like 100,000 users drop in, like, do I have some throttling, caching, or something that I can do so that don't drag my server down? Or like, do they send deltas or something?
I mean, we don't, at the moment, have kind of operational tooling for sort of managing data throttling of the replication pipeline. It's open source Elixir code, so I mean, you could implement some strategies in sort of getting into, like, we have a Broadway pipeline, and you could kind of, if you were operating on that kind of load, you could introduce some mechanisms for sort of rate limiting and just slowing down the replication stream. But I guess just in terms of maturity of the project, like, we're still really working to first base to deliver on the sort of core combination of features, and there's quite a lot of sort of productionization challenges which we would see coming next.
This would go like, this would go Postgres, Broadway, intermediate, then to the front end.
I mean, I guess if you were having an application that's talking directly to Postgres, then that's slightly out of kind of, that's sort of, you know, how you manage the scalability of that would be out of the scope of the electric system. If it's more like, for instance, you have users signing up through the local first application, that's generating a very high load. Is that something that you want to be able to sort of control in terms of just making sure that the data flows don't overwhelm the system? That's something that is perfectly possible to build into the way in which you would operate the software. And it's quite easy to instrument, and we have instrumentation and telemetry. But basically, you would have to build out your own. At the moment, we don't have anything built in yet around something like throttling or kind of auto-scaling.
Thank you for the great talk and also the live demo. My question goes to the states where there's some conflict. You mentioned that you have some means of avoiding conflicts, but I still would like to ask if there is some tooling or some authority that when the conflict is created somehow, that needs to be resolved somehow manually or something like that. How do you deal with this?
Yeah. So, I mean, there's quite a few different sort of strategies with this kind of thing, and we're sort of more towards the automatic conflict resolution side. So we haven't built the system at the moment to have a especially expressive kind of manual conflict resolution flow. But what we have done is whenever there is a concurrent merge applied, we write that into a conflict log. And that conflict log can is in Postgres, and it can stream onto the local devices. So there is the minimum primitive required to be able to basically, if you wanted to, you can monitor that log, look for kind of any sensitive merge logic which may have resulted in a state that you wanted to undo, and then you can undo that.
Okay,
but I think,
thank you.
But I mean, it's worth noting that, for instance, some of the work from Ink and Switch recently on this has been looking at like different types of workloads with, say, sort of different frequency or kind of periods of sort of real-time collaboration. And for kind of longer collaboration and things like there are more sort of Git-like workflows. And at the moment, that's not stuff that we've optimized for, and there's maybe other tooling that does. Whereas we are more like this sort of like regular stream of small transactional stuff where there's rare conflicts, and we're optimizing for just sort of ease of use and automatic conflict resolution.
One second.
I don't own the front end.
Can you
What
hear?
if I'm not the consumer of my API? Do I have to still build this classical RESTful API, or can I just tell my clients, hey, download the ElectricSQL client?
Yeah. So there's basically a protocol buffers there's a protocol which we call the satellite replication protocol between the server side and the front end. And then we have a main TypeScript client, which is like a kind of client side of that protocol. There are now community contributed clients for Dart and Flutter, and we're developing one in Rust that we can then compile to different languages. So it's perfectly possible to basically build anything that you want on top of the same protocol buffers protocol. So you could build any type of sort of client environment or any type of application, and that's a kind of documented sort of standard protocol which would allow, in a sense, any application to build on this. I mean, if it was more a case of just, is that what you meant in terms of almost like someone else wants to build their own client app that somehow can integrate with the system? Yeah, because I mean, otherwise, of course, they could also just use the standard client libraries. I guess it depends on the environment that they were looking to work with. You also have, sorry, just one thing is that you also have the ability, so we have this TypeScript client, and for example, it can run in Node. So on some of the deployments that we've done, we run a Node sidecar process alongside, say, an SQLite database. So if you wanted to, you can have another application that just talks to the SQLite database. You then run this Node sidecar, and everything just syncs into the kind of system, basically. So there's a few different ways. You can either sort of build your own client integration, or you can just use the relational database access to basically sort of put data into the system.
And could I set specific permissions for specific clients?
Yeah.
On my own app can write everyone else.
Yeah, yeah. The permission's very expressive, and you would just have like the replication connection is always authenticated with a JSON web token. That JSON web token sort of comes out of your own system, so you can kind of put whatever rights you want in that. In the database rules, you can express any kind of logic you want around roles and permissions. So you could grant a third-party application just specific write access, even on a kind of row-by-row basis.